hints to fluid-rock interaction processes happening at depth in these systems. There's a lot of stories around that these fluids are super aggressive, that they're loaded with solutes, and so on and so on. And an understanding of how the chemistry works on that will probably be instrumental to actually make it work, because then you can handle the chemistry. Now, the problem that we are facing is we cannot model this chemistry very well. Those of you who were there yesterday, they saw Eric Sonnenthal's talk, who showed the dilemmas you're facing when you try to do reactive transport. And it sounded a bit like we don't have enough experimental data. That's true. But what I want to highlight here is that we are facing a much more fundamental problem, and that's actually we have no theory at the moment for describing solute thermodynamics at supercritical conditions relevant to geothermal operations. So we simply cannot model it because we have no equations to describe the thermodynamics, the chemical thermodynamics of supercritical fluids. And this is a lack of theory and experimental data, because you would need these ones to inform the equations to compute the right things. But there are some current efforts on the way to overcome these several decade-old gaps. And I hope I can convince you that we are on a good route towards finally overcoming this. Now, as a little teaser, I already mentioned silica scaling. If you have a conventional high enthalpy operation, yes, silica is known to be something that can affect your operation, but in essence, engineers, chemical engineers and others have managed to overcome it, and it's actually thanks to favorable kinetics of silica in these fluids. So you can even dispose the water, let the silica coagulate, and then make money out of that with people bathing in there, like the Blue Lagoon here in Reykjavik. So it's not a really big problem in these operations. Now, in contrast, this is an image from IDP1 flow testing. Just after 40 days, the pipes have massive silica scaling. And you can, 14 days is not what you want to have for an operation. This you would want to have maybe after 20 years, but not after 14 days. And the interesting thing is, when you look at it, this happens from a very low silica fluid. Let me get laser pointer here. So in these fluids in conventional systems, you have relatively high silica, but you can manage scaling. In superhot systems, you have very low silica, but you can get massive silica scaling. So these two things are sort of just at the opposite end of the spectrum. And the question is, why is that the case? And can we actually calculate and predict how that comes and what to do against it? Now, just as a diagram here, on the vertical axis is silica content. This is quartz solubility here. So this is temperature on the horizontal axis. So here is 400 degrees, 500 degrees. Somewhere here is the critical point of water, and the different curves are quartz solubility at different pressures. So you see at high pressures, high solubility, and the normal behavior, i.e. the higher the temperature, the higher the solubility. But when you go to here, to the critical or supercritical region, you see that actually silica or quartz solubility massively drops when you come into this region where water has low density. And actually, if you take IDP1, it would just plot here on the bottom of the graph at 450 degrees. You would have to have a log scale on the vertical axis to actually get the silica concentration. So it's very low silica concentration. And nevertheless, because you have these super high mass flow rates and it's a fact of depressurization, you get the scaling and you cannot really handle it yet. So we lack a thermodynamic formalism to deal with supercritical solute chemistry, and that's a fundamental thing. Many people think, well, then I use a different software and I can calculate it. No, it's not a problem of the right software. Whatever you use, Freaksy, Tough React, GEMS, you name it, it will not be able to calculate this. And I will stress this several times during the talk. And we lack experimental data to parameterize such formulas if we have them. So you see here's a big gap in data just where we need them. There's some things on the way. Andri will talk in his part later on some recent experiments they're doing in the GeoPro project, and that's actually really, really needed. All right, some background to understand that. In order to understand the chemistry that we face in these fluids, we have to understand the water properties, because water is the solvent as a function of temperature and pressure. Here's two versions of the water phase diagram. Top left is in temperature, pressure coordinates. And as everybody knows, there's the boiling curve, and it terminates in the critical point. Along the boiling curve, liquid gets less dense towards the critical point, and vapor gets more dense, gets denser. So, and at the critical point, water cannot decide anymore whether it wants to be a vapor or a liquid. And we will see this later on. There is fluctuations on the molecular scale. You will have domains of more liquid-like properties inside your critical water and more vapor-like ones. And these gray lines here are isocores, so lines of constant density in kilograms per cubic meter. So this 950 would be 0.95 grams per cubic centimeter. And you see it's pretty steep. So that means if you increase pressure, or you have to increase pressure a lot to compress the water. Now, if temperature increases, density decreases, that's as expected. But the slope here doesn't really change a lot. The liquid part here is still quite incompressible. Then comes this dashed line. That's what water, the density that water has at the critical point, which is 322 kilograms per cubic meter, 0.322 grams per cubic centimeter. And then below this, you have more steam-like, dense steam or vapor-like densities. And you see these things become much more shallow in their slope. And that means this stuff is more compressible. And even in particular, when you go to the critical points, all these isocores actually come, or a lot of them come very close here near the critical point and merge at the critical point, which means you have very high compressibility here. Now, if you have a look at this, this means high density here, low density down here, and that affects the chemistry. This also means high solubility for most minerals and salts, or comparatively high solubility in this region, low solubility here. And that means depressurization here would precipitate minerals, or increase of pressure would dissolve them. Now, one more thing about this. I said already here at the critical points, the isocores get close to each other, which actually means it's very, very compressible. A little change in pressure here, you see, can go from 600 kilograms per cubic meter down to 100. So very compressible, actually, vice versa. And if you, that means actually, if you plot the isobaric compressibility, isothermal compressibility of water, you get these curves. So here is temperature. Critical temperature is about here. This is the compressibility on a log scale. And these are various isobars, lines of constant pressure. And this thing here is actually the boiling curve. So this is the liquid branch, comes up here along the boiling curve, and this is the vapor branch, and they join here, and you see this incredible peak. It goes to plus infinity. And that's actually the compressibility at the critical point. So at the critical point, water is infinitely compressible. Sounds esoteric, but isn't. Of course, as soon as you start to compress, you're not at the critical point anymore. You end up here. In a real system, infinity is not the case. But this property itself has important implications. And also you see at 250 or 300 bars, there's still a peak in compressibility. So that makes these fluids quite special also in how to handle their flow. Now that's the second coordinate system here, pressure increasing downward, specific enthalpy on the horizontal axis increasing to the right. And that's a diagram very much liked by reservoir engineers. What you see here is isotherms on that. They have this shape at the low temperature region, 100, 200, 300 degrees, they're essentially vertical. And when you approach the critical point, you see they're bending around here. And at the critical point, at 374, the isotherm would be horizontal at the critical point. Which means when you look at the heat capacity, which is the derivative of enthalpy with temperature, this would again be infinity. So heat capacity, isobaric heat capacity, has a plus infinity peak at the critical point, and it has quite some extrema at other pressures in the critical region. So all these properties show some extreme behavior near the critical point, and this has made supercritical and critical fluids something considered very esoteric and difficult to handle. And that actually carries through to the chemistry. This is most impressively seen if you look at hydrothermal geochemistry's workhorse. That's the so-called HKF, Helgeson-Kirkham-Flowers, after the inventors or the scientists who invented that model, also called an equation of state that is implemented in the subcrit software. And in temperature, pressure coordinates again, so this is temperature on the horizontal, pressure on the vertical axis. This formalism can be used to calculate the properties of dissolved materials, of solutes, wherever this diagram is white. And what you see is actually there's red areas, and in these red areas, it's not applicable. Those again who heard Eric talking yesterday, he spoke of some magic 0.35 grams per cubic centimeter, below which it was impossible for him to get some results. Well, that's the very reason. HKF is at the fundament of these thermodynamic databases that are being used, and it's not applicable below this. If we put some of the more important types of hydrothermal systems on Earth onto the diagram, it can be magmatic hydrothermal systems, i.e. such that form porphyry copper deposits. That's this MHS bounded by this box. Mid-ocean ridge systems bounded by that box approximately, or deep roots of geothermal systems. That's what we're talking about here. That's the yellow thing. They're all in the heart of the red region. So you cannot use our normal workhorse to calculate. And unfortunately, there is no alternative, or hardly any alternative, that would work in here. So we have no tool. Again, HKF is not applicable to important types of hydrothermal systems, and in particular not to superhot geothermal. That's the yellow box here. The limitations are strongest for anything that has ions, and that's in the near critical region here. And supercritical low-density fluids, that's the ones that we encounter here. The reason is that the physical concept that was used to develop HKF breaks down in this region. So the assumed physics behind how you calculate the energies, the chemical interaction energies, is wrong when you go into the deep red region. And for that reason, you cannot fix it by extrapolating or adding a few parameters. It's a fundamental problem of this thing. Again, no matter what software you use, it cannot do it because all of them use HKF. And if HKF provides wrong data or cannot calculate it, then your software cannot help you. So it's not a software problem, it's a fundamental thing that we have to overcome. So what's the problem there? Let's have a look at this diagram. On the vertical, so it's for the self-ionization of water. So H2O goes to H plus and OH minus. That's the thing, that's the reaction that controls what is neutral pH. On the horizontal axis is temperature, and on the vertical axis is the logarithm of the equilibrium constant for this reaction. You see here at 25 degrees and 1 bar, so at boiling pressures it's 14. That's what you know. pH range at ambient conditions is from 0 to 14. And neutral pH is just half of this value, it would be 7. And you see if you vary temperature and pressure, so the long dashed lines are isobars and the thin dashed or the short dashed lines are isocores. You see there's a strong variation of what is neutral pH. If you're at high temperatures and high pressures, you can have a neutral pH here of 3.5 or something like that. Or if you are in a super hot geothermal part, you may actually have a neutral pH of 8 or something like that in your fluid, or 9 or 10, depends how low your pressure is. What you also see, so here's the critical point, all these curves become super steep and at the critical point actually vertical. So it's very difficult to capture this accurately, not to speak of doing the experiments that capture this accurately. The small error in the horizontal or vertical axis makes very large errors in your chemical calculations. And so this is the problem, how to capture these curves that they are accurate. So as theory for understanding these trends has been lacking so far, and pretty simple, no theory, no accurate equation. Okay, now let's revisit that point and see that there is probably a way out of this dilemma. So this is basic chemical thermodynamics. Those of you who ever had chemistry, physical chemistry, had this in their first course probably. Usually we work with the Gibbs free energy of reactions. And basically that's what you want to calculate in order to determine if reaction can progress in the one or the other direction. And typically you have a reference value at some temperature and pressure that has been measured for some particular conditions, and then you need to add this term here to get it. And K is the so-called equilibrium constant. What's that? For example, if we have the reaction of sodium feldspar with potassium chloride from the fluid, it would form potassium feldspar and release sodium chloride. Then the equilibrium constant is basically the ratio of the concentrations of the aqueous species there, or components. The concentrations of the solids you can skip. As long as that thing is present, it's considered to be 1. And so the equilibrium constant is this ratio, which is also used as a thermometer in geothermal exploration, the sodium-potassium ratio, or vice versa, of the fluids you sample at hot springs. So then at equilibrium, this thing, there is no free energy left. These and these things have reacted, so it's balanced out. So this is 0 now, which means that this standard property equals this term here. And this term you can actually calculate as the sum of the Gibbs free energy to form the products minus the ones for the reactants. Now, the delta G's are not provided by thermodynamics itself, but it has to be determined by experiments. And the data are tabulated or fitted with equations derived from physical models. And these are also known as thermodynamic models, such as HKF. Now, what happens when you have such a thing? You usually have a reference value, and typically this is at 25 degrees C and 1 bar. And it's considered at infinite dilution in liquid water, because that has some advantages. If you then have experimental data or some theory, you can integrate going from here to some higher temperature. And for integrating this, you need some heat capacity terms, which you convert to entropies, etc., etc. But basically, you integrate over heat capacities here. Then typically your pressure is higher than 1 bar, so you have to go to higher pressures. And for getting this, you need to integrate volume terms, partial molar volumes. Then you add temperature and pressure, and maybe you have some finer concentration. And to get to this, you have to integrate a so-called activity model. Now, that's usually the most nasty part. So HKF and these things, they focus on the front side here, so the temperature and pressure dependence, and this is left to something else. Now, this seems all pretty straightforward, but the downside is if this thing here, temperature and pressure, is near the critical point of water or in the broader vicinity, then the equations you have to integrate or the trends you have to integrate here, they're not well behaved anymore. So this is an example, the partial molar volume of gases in water or of sodium chloride, and approaching the critical temperature of water. And you see it's going to very high values, effectively to plus infinity for the volatile solutes here, or to minus infinity for a non-volatile solute. And this is pretty nasty, because if you want to integrate it, you have to catch the exact shape of this curve very, very well. And before you can catch it, you have to have experimental data that are able to constrain this curve in the first place. And this is basically almost impossible already. So if you do the integral on this with a wrong formulation, you will be massively wrong and your calculations will be quite erratic. So for the exact curve, you would need a theory that predicts the mathematical form, and we're back to step one. Well, are we? We can have a look at why HKF fails to do that. And there is a simple molecular scale explanation. HKF is based on the so-called Born model invented by Max Born, a German physicist, I think in 1910 or so. And he considered the free energy that you have when you have an ion in water is simply taking this ion out of a vacuum and inserting it in some model water, which is basically simply a homogeneous dielectric medium. And then the electrostatic interaction between the ion and this dielectric medium would be the main part of the free energy. Then Helgeson and Fellows have augmented that with a number of empirical terms, and then they called it the semi-empirical HKF model. If you look at the partial molar volume, that's the equation. And basically, almost all of that in here is essentially empirical and was found by trial and error with some guidance from the Born model. In real solutions, it doesn't look like this at all. You insert an ion into water, you have water molecules, and that's all these little teddy bears here with negatively charged oxygen and positively charged hydrogens. So if there's a positive charge here, the oxygens will turn towards it and form a so-called hydration shell that's pretty tightly bonded. This is a small and highly charged cation. And so the properties of water near the ion will be different from further away. In particular, if you are in the compressible critical region now, this is maybe, for example, a local constriction of the water. It gets denser. And then this density perturbation that you have here will propagate to further away, leading to these large negative partial molar volumes. So in essence, this will impose some pressure volume work term as a major contribution to the free energy. Actually, at the critical point, it's almost all of that is pressure volume work. So this can in principle, or should in principle, be possible to capture with some theory. But it gets even simpler if you're stepping back. So we had just this complicated formula for the partial molar volume in order to be able to calculate the pressure dependence. So let's review what is actually the partial molar volume of a solute. So that's in this little diagram here. On the vertical axis is molar volume of your solution. And on the horizontal axis is the concentration of whatever you want to dissolve in water on the mole fraction scale. That allows you that this ranges from 0 to 1. 0 would be pure water, 1 the pure substance of what you want to dissolve. Now, at 0 concentration, obviously, it's pure water, and so the molar volume is well known in pressure and temperature. There's super accurate equation for state. Then as you start adding solute to it, the molar volume will change, maybe following a curve like that. And if you want to have the partial molar volume at infinite dilution, it's just the tangent to this curve. You take this tangent and extend it to full concentration of the solute, and then this intercept here is called the partial molar volume. So geometrically, that's super simple. Means this partial molar volume is this volume of water plus the slope of this curve times the distance traveled, which is 1, so you can kick it out. So V2 is V water plus dV dx. Since this is a finite term, can only be this guy that makes all the problems with this divergence at the critical point. So then it would essentially be, upon adding a little bit of solute, actually the volume would drop massively and you get this very large negative partial molar volumes. Now then some smart people like Anneke Level-Sanger said, well, let's do some simple basic mathematics to that. Let's use the chain rule and expand this term. So dV dx can be expanded as dV dp. So the change in volume of pressure times something called the Krichevskii parameter, which is dP dx at constant volume and temperature. And now, when you look at this, this is basically compressing pure water here in this limit. So it's related to the compressibility of pure water. And if you had a 1 over V in front of it, it would be the compressibility beta water. So you can rewrite this whole thing as partial molar volume of the solute is molar volume of water times 1 plus compressibility of water times this thing. And compressibility of water, I showed you this before, has this nasty behavior to be absolutely misbehaved, poorly behaved at the critical point. It goes to infinity. So it can now be shown that all these divergence of the partial molar volume is due to this guy. The bad guy is the compressibility of pure water. So there's nothing magic at all. It's just you insert an ion, it breaks the water structure, and this local perturbation is propagating through the infinitely compressible thing there, or highly compressible thing if you're not exactly at the critical point. And this is very, very well known from equations of state. So we can actually take out this extreme behavior out of partial molar volumes, etc., by just knowing this and looking at this equation. So to summarize this, there is no supercritical thermodynamic black magic. It's the isothermal compressibility of pure water that's responsible for the mass. And then there is this thing, the PDX, which is called the Krichevskii parameter. And it's believed to be well behaved and represents solute-specific interactions. So if we understand the behavior of this guy with temperature and pressure, we can do thermodynamics of solutes even in supercritical or critical water. Well, then people in the late 90s and early 2000s, there was quite some activity on that. And for electrolytes and non-electrolytes, on the horizontal axis, we have always solvent density. On the vertical axis, this Krichevskii parameter. And these are near critical temperatures. That's from molecular simulation from Ariel Chialvo and colleagues. And I had the luck to be in that working group back then. And it shows it's a super well-behaved property. Same thing for some non-electrolytes. I don't remember which ones these are. This is probably methane, and this is maybe CO2. And again, they show very nice behavior as a function of temperature. So if we can get a handle on how this behaves as a function of temperature, pressure, and solute type, then we are done. Now we have this Horizon 22 project GeoPro where we're trying to do this. And this is an example. There is one equation of state by Joseph Sedelbauer and O'Connell and Wood, published in 2000. Where they actually tried to overcome the limitations of HKF by introducing a Krichevskii-based approach. And I took this and plotted it as a function of isocores. So each of these lines here is an isocore. This is, I don't know, probably 200 kilograms per cubic meter, 300, 400, 500. The small ones here are up to 1,000 kilograms per cubic meter. And plotting the Krichevskii parameter divided by temperature against 1 over temperature times our compressibility gives this nice straight lines for quite a range of temperatures. And it holds for non-electrolytes as well as for individual ions. So assuming they did a good job in parameterizing that, there seems to be a route that gives nice behavior for non-electrolytes and electrolytes with some pretty simple relationships. So this is ongoing. We're trying to understand the systematics behind it. And there's actually a nice thing that you can add on top of that to better understand it. I just want you to pay attention again to this formula. Here is this term compressibility times dpdx. And this is just very generic on the macroscopic scale. Now we turn to the molecular scale. And if we look at a near critical water, schematically it might look like this. You have all these individual teddy bears. Here are again water molecules. You will have domains that are more liquid-like, more dense, and domains that are more gas-like. And if you have now a gaseous non-volatile or volatile solute, it will prefer to sit in these gaseous domains, and an ion will prefer to sit in the more dense things. And this actually is already the explanation for the partial molar volumes. This one prefers the dense ones, so it will be in the more contracted ones. This one will be in the more expanded ones. So on average, this sees more water molecules near to it, and this gives, and I will show this on the next slide, a negative, and this will be a positive partial molar volume. So if you do molecular simulation, you can obtain what we call the radial distribution function. That's G of R here on the vertical axis. And on the horizontal axis is distance from a single molecule. So you run the simulation, you look how the molecules move around, and then you let the computer analyze how many water molecules were sitting next to it. And then you normalize it by the average density and radial coordinates and so on, and you see this. If you have water, the red water will have on average more water molecules just next to it than the average density of the fluid would predict. Average density would be 1, so there's a strong binding, that tetrahedral binding that holds the nearest neighbor water molecules. That's this peak. There's a weak second peak here for these conditions. For example, sodium and oxygen, it makes a very strong interaction and will bind these first few water molecules strongly to the sodium ion, or in the case of chloride, that's a bit bigger. There's also somewhat weaker thing than this. Now what you can do is you can integrate this radial distribution function as a function of radius here, with radius. And then you get actually the accumulative number of water molecules that surround the central particle as a function of distance. And that looks like this. So again, here, these things are exactly this radial distribution function. And the red curve is now the integral of the red plus the green curve. So that's how many water molecules as a function of distance surround NaCl. That's the red curve. If you do the same thing for pure water, that's the blue one. And you see they're not identical. There is a separation. If you plot this difference here as a function of distance, it's this pink curve here. And that's what we call the excess number. So around the NaCl, there is more water than it would be around a water molecule in pure water. And here you see it's about 6 or something like that. Now this excess number is actually just minus the term that we saw before, compressibility of water times the Krichevskii parameter. This is easy to show mathematically. And so we can now use molecular simulation to understand why this thing has the values it has. Of course, molecular simulation is not advanced enough to get the exactly accurate numbers, but we can understand the trend. Why is it linear with this, and so on and so on. And this is currently ongoing in GeoPro. That's University of Cologne with Max Schulz and Sandro Jahn doing this. So we're trying to bring together a molecular scale fundament with experiments that Andrei will report about later in order to derive hopefully a new model that can then succeed HKF. So this is pretty much related to what people have tried in the past, so-called density models. So this is my just last slide on science before I conclude. We have seen this before. We saw these nasty curves. And this was because we plotted it as a function of temperature and pressure. If you do this instead as a function of density and log density of water and temperature, for example, or the equilibrium constant, then you see usually linear trends, which is much nicer to handle than this and probably also easier to extrapolate. This holds for silica solubility. That's this diagram. You see very nice trends, the individual temperatures here, log density of water. Very nice. This holds for this thing here. Again, you can plot it as nice isopores, or also for ion association if you have Na plus and Cl minus going to a neutral NaCl, and the solution does the same thing. So this is possibly the easiest outcome of this, of how to parameterize further things, but it's tedious work, digging out all the experiments, reviewing them, and trying to parameterize it. To conclude, so currently supercritical fluid chemistry cannot be modeled no matter what software you use. So no illusion, if you use the other code, you cannot do it. It's a fundamental thing, and because this fundament is not there, no theory yet to describe solute thermodynamics in the supercritical region we are so interested in. And on top of that, there's very little of no experimental data for relevant TP conditions. Again, Andrei will later speak about some nice experiments ongoing. But there's some light at the end of the tunnel. I mean, the previous work of Annika Level-Sengers and I'll really demystified these supercritical thermodynamics problems. Pure water is the bad guy, and we know this very well, so we can hopefully use the equations I showed to extract or to abandon this contribution and then focus on the real thing. There are some nice links between macroscopic and molecular scale properties that facilitate developing new equations of state, and that's what we're trying at the moment in order to be able to really contribute some calculations in the near future. But obtaining these results and the experimental data is quite a labor-intense thing. So then funding is just required in order to pay people to do it. So I'm done, and I hope I could give you some ideas what the problems are that we are facing. Thanks.